Now, one last thing that I want to add here is that in that last problem, we had a point where the second derivative test came back not enough information. I found a critical point. I calculated the second derivative, evaluated at the critical point, and I got 0. So the second derivative test only helps me if that second derivative is actually positive or negative. So places where the function is concave down, concave up, or concave down. So if that happens to you while you're working on one of these problems, you're going to have to go back to using the first derivative test. So here is another example. Here's a function. F of x is x to the power 2/3 times the quantity 6 minus x all to the power 1/3. And here we have calculated our first two derivatives using the product rule and then later the quotient rule. And we build up this nice table of values in our scratch work. So the coordinates that give us critical points, right? What values of x make this first derivative 0? And also what values of x make this first derivative not exist? Well, if I put in x equals 4, this fraction, this quotient rather, will be 0. If I try putting in 0 or positive 6, then the quotient will just not exist because I'm trying to divide by 0. So we have 3 different critical points, or critical numbers if you prefer. And I can't actually put those into the second derivative either. I cannot evaluate the second derivative at 0, because then I'll be dividing by 0. I cannot evaluate that second derivative at 6, because then that quotient will be trying to divide by 0 again. So I've got to go back to figuring out, is the first derivative negative or positive on each of these sub-intervals, where we're splitting it up at the coordinates 0 and 4 and 6. So less than 0, the derivative is negative. Between 0 and 4, the derivative is positive. Between 4 and 6, the derivative is negative. And above 6, the derivative is negative. So that information tells me that I've got a, well, I'm decreasing, then I increase again. I've got a minimum here, a local minimum. Then later on, I am increasing and I stop increasing and I decrease instead. I've got a local maximum. Then I've got a decreasing function, and then it'll stop decreasing, and then it decreases again. Not a minimum or a maximum, just a false positive. So this is describing all of what I said in printed text. And again, we could have used the second derivative in some of those places, but not for x equals 0 and not for x equals 6. The function actually looks like this. So notice here are critical points where the derivative fails to exist. Derivative fails to exist here for a vertical tangent line. And then here I had a horizontal tangent line, which gives me derivative equal to 0. All 3 of those are critical points. We have a local minimum here at 0. Even though we have this sort of pinch point like that. We have a local maximum up here at x equals 4, and that is it.